time. And before I deliver my opening remarks, I want to note that the committee today is meeting virtually. I hope for not much longer, but today's still virtual. I want to announce a couple of reminders to the members about the conduct of this hearing. First, members will please keep their video feed on as long as they're present in the hearing. Members are responsible for their own microphones. Please also keep your microphones muted unless you are speaking. Finally, if members have documents they wish to submit for the record, please email them to the committee clerk, whose email address was circulated prior to the hearing. So good morning and welcome to today's hearing on accelerated deep space travel with space nuclear propulsion. I want to welcome our panel of impressive expert witnesses today. We're very excited that you accepted our invitation and thank you for being here. If we're serious about deep space exploration to Mars with humans, which I am serious about, I know everyone on this committee is, we need to take bold steps to make it happen and make it sustainable. Today, we're talking about one bold effort that could get us much closer to achieving that Mars goal, space nuclear propulsion. Space nuclear propulsion can produce thrust far more efficiently than conventional chemical systems, allowing for shorter trip times to Mars. Why does this matter? Well, one reason, of course, is that shortening the trip reduces the risk of space radiation exposure for astronauts. Another is that, depending on the technology used, space nuclear propulsion may enable more frequent trips to Mars than the typical 26-month intervals that rely on favorable Mars-Earth alignments. Reducing that 26-month interval increases mission flexibility to enable both cargo deliveries and human missions to Mars. However, building an operational space nuclear propulsion system is hard, and the technical challenges are many. Choosing a nuclear fuel type and source, developing a space-qualified fission reactor, developing the requisite materials and infrastructure, and carrying out the testing, all while managing the required safety protocols for nuclear activities, are just a few examples of those challenges. To date, the US's use of space nuclear technology has been in battery-like radioisotope power sources for probes, traveling to distances where sunlight is insufficient to produce power for the spacecraft. But when it comes to propulsion, the United States has yet to fly a fully integrated space nuclear propulsion system in space. Government work on space nuclear propulsion dates back to the 1960s, but it was curtailed in the 1970s, and then follow-on efforts have largely been intermittent since that time. That prior work, however, provides a foundation and a baseline that's still useful today. A recent NASA commissioned National Academies of Science, Engineering, and Medicine study on space nuclear propulsion found that a system could be ready to support a human mission to Mars in 2039. Mr. Purwood would prefer 2033, but only if we act aggressively now. According to the study, the required space nuclear propulsion systems would need to be available in 2033 for advanced cargo emplacement and risk reduction prior to a human mission. And that's slightly more than 11 years from now. So if the US is serious about leading in a human mission to Mars, we have no time to lose. Congress has prioritized development of nuclear space propulsion over the past several years, directing about $100 million annually for NASA to advance nuclear thermal propulsion capabilities with the goal of conducting a future in-space flight test. I hope that today's hearing we can examine what progress NASA has made with these dedicated investments and what further investment is needed in order to achieve the human to Mars goal in the 2030s. And how can NASA leverage other contributions, whether from different parts of the US government or from commercial industry, to reach that goal? Because NASA is not alone in seeing the potential for space nuclear propulsion. The Defense Advanced Research Projects Agency, DARPA, has its own nuclear thermal propulsion project, albeit for national security interests. And the Department of Energy, with this nuclear expertise and infrastructure, is also involved. We need to see how the various agencies are collaborating, including on a government-wide strategy and vision for space nuclear propulsion. So the time to act for America is time for America to act and take bold, well-considered steps towards the goal of sending humans to Mars, a goal that will both inspire and lead to significant technological advances that will benefit all of us here on Earth. Development of space nuclear propulsion is one such necessary step, and this subcommittee has an essential role in setting the policy to get us there. So I really look forward to our witnesses' testimonies, and I now recognize my friend, the ranking member of the subcommittee, Dr. Bhavya, for an opening statement.
Thank you very much, Mr. Chairman. This is going to be a very interesting, and I'm looking forward to this hearing. Space nuclear power and propulsion holds great promise. It could lead to faster travel times, less radiation exposure for astronauts, greater mission flexibility, and more power for operations and instruments. Other nuclear applications like surface reactors could also support a robust space exploration architecture. Nuclear power and propulsion for space exploration is not a novel concept. The Air Force, the Atomic Energy Commission, and NASA partnered in the 50s and 60s on Project Rover and the NERVA program to develop nuclear rockets. The SNAP program resulted in the launch of a nuclear-powered satellite in 1965. The Russians flew Topaz reactors in the 80s and 90s, and NASA has incorporated radioisotope power systems into missions since the dawn of the space age. Support for new space nuclear projects have come and gone over the years as well. The space reactor prototype was canceled in the 90s. Nuclear projects associated with the Strategic Defense Initiative and Space Exploration Initiative faded with the overarching programs, and Project Prometheus was canceled due to budget constraints 15 years ago. If future programs are not crafted carefully with strategic forethought, they may fall victim to the very same fate. As the National Academies have pointed out in their report from earlier this year, recent apples-to-apples trade studies comparing NEP and NTP systems for a crewed mission to Mars in general and baseline mission in particular do not exist. The Academy also called on NASA to conduct an objective comparison of the two systems. Other decisions, such as whether HEU or HALEU should be used as the fuel, and whether HAL, MPD, or VASMIR should be used for NEP thrusters should also be studied further. Extensibility, or the ability of a system to be used for future missions and not be a dead-end technology, will also be very important for the future viability of nuclear space propulsion. Architectures developed for crewed missions, uncrewed mission, surface power, low Earth orbit operations, and missions to the moon, Mars, and beyond should all build upon each other and leverage previous investments. These space architecture trades should not only meet near-term goals, but also account for future exploration challenges. What might seem ideal in the near term may not be the very best solution in the long term. And when budgets get tight and funding gets prioritized, high risk, high reward technologies like space nuclear power and propulsion have often been left on the chopping block. Because of this reality, NASA should evaluate extensibility in future strategic decisions regarding space nuclear power and propulsion architectures. Coordination with other agencies and the private sector will also determine the success of space nuclear power and propulsion research and development. The Department of Energy has an advanced reactor demonstration program and a nuclear reactor innovation center. DARPA initiated the DRACO program. The Strategic Capabilities Office started the PELI project, and DIU issued a solicitation for small nuclear powered space engines. Furthermore, companies like BWXT, X Energy, USNC, and General Atomics have proposed technologies that may meet NASA's space exploration needs. For NASA's space nuclear power and propulsion efforts to be successful, they will have to coordinate with these other efforts. Space Policy Directive, Policy Directive 6, the executive order promoting small modular reactors for national defense and space exploration, and the presidential memorandum on launch of spacecraft containing space nuclear systems were issued by the last administration to enable this coordination. But oversight will be necessary to ensure that the agencies follow through. Adhering to the national strategy with consistent, steady, and predictable investments, coordinated partnerships with other agencies and the private sector, and a strategic perspective for exploration will all influence whether space nuclear power and propulsion will live up to its promise. I look very much forward to hearing from our distinguished witnesses today, and I yield back the balance of my time as I see it. I'm at the end. So I yield back. Thank you.
Thank you, Dr. Babin, very much. So if there are members who wish to submit additional opening statements, your statements will be added to the record at this point. And this time I'd like to introduce our witnesses. Dr. Roger Myers is a senior aerospace consultant with more than 30 years of experience in space technology development, flight programs, and in-space mission architecture planning. He previously worked at Aerojet Rocketdyne and held positions at NASA's Glenn Research Center. Dr. Myers also served as co-chair of the National Academies of Science, Engineering, and Medicine's Committee on Space Nuclear Propulsion Technologies. He holds a PhD in mechanical and aerospace engineering from Princeton University. Dr. Bhavya Lal is senior advisor to the NASA Administrator for Budget and Finance. Previously, Dr. Lal led the Space Technology and Policy portfolio at the Institute for Defense Analysis, Science and Technology Policy Institute, where she led analyses for the White House Office of Science and Technology Policy, the National Space Council, and federal government agencies. She has served on National Academies committees, including on the Committee on Space Nuclear Propulsion Technologies. She holds a bachelor's and master's degree in nuclear engineering, a master's degree in technology and policy from MIT, and a doctorate in public policy and public administration from George Washington University. Mr. Greg Meholic is a senior project leader for civil systems technology at the Aerospace Corporation, a federally funded research and development center dedicated to the nation's space enterprise. Mr. Meholic is the technical coordinator for cross-agency projects associated with fission-based space nuclear propulsion and power. His portfolio includes launch vehicle concept development and advanced propulsion technology planning for future access to space. Mr. Meholic holds a bachelor's and master's degrees in aerospace engineering from Embry-Riddle Aeronautical University. Mr. Michael French is vice president for space systems at the Aerospace Industries Association. He previously served as a senior vice president for commercial space at Bryce Space and Technology and has held federal government positions, including as NASA's chief of staff. Prior to serving in government, he practiced law in the defense and aerospace sector. Mr. French holds a Bachelor of Science in Business Administration from the University of California, Berkeley, and a JD from Harvard Law School. Dr. Franklin Chang-Diaz is chairman and CEO of Ad Astra Rocket Company, to the stars. A former NASA astronaut, Dr. Chang-Diaz flew on 7 space missions and completed 3 spacewalks. Dr. Chang-Diaz initiated the Vasimir Plasma Rocket Engine project in 1980 at the Johnson Space Center. In 2005, he retired from NASA and founded Ad Astra to continue to mature the technology through the private sector. Dr. Chang-Diaz received a PhD in applied plasma physics from MIT and a bachelor's degree in mechanical engineering from the University of Connecticut. As our witnesses should know, you'll each have 5 minutes for your spoken testimony. There's a cool little clock on the Zoom screen, and your written testimony will be included in the record for the hearing. And when you've all completed your spoken testimony, we will begin with the difficult questions. And each member will have 5 minutes to question the panel. So let's begin with Dr. Myers. Dr. Myers, the floor is yours.
Good morning, Chairman Beyer, Congressman Babin, and members of the committee. My name is Roger Myers. I'm the owner of R. Myers Consulting, the president of the Washington State Academy of Sciences, and the chair of the Washington State Joint Center for Aerospace Technology Innovation. I served as the co-chair, along with Dr. Robert Braun, of the Committee on Space Nuclear Propulsion for Human Mars Exploration of the National Academies of Sciences, Engineering, and Medicine. NASA's Space Technology Mission Directorate commissioned this study to assess the primary technical and programmatic challenges, merits, and risks for developing and demonstrating space nuclear propulsion systems for human missions to Mars, including both nuclear thermal and nuclear electric technology options. Specifically, we were asked to assess these factors for a nuclear thermal propulsion system providing 900-second specific impulse and a nuclear electric propulsion system providing at least 1 megawatt of electric power and a power to mass ratio that is substantially better than the state of the art. Additionally, the propulsion systems were to be ready for a human mission in 2039 with a round trip time, including Mars surface stay, of less than 750 days. Based on the input that we gathered and our committee deliberations, we arrived at several consensus findings and recommendations. I will discuss only the most important of these in my oral testimony because of time limitations. They are all addressed in my written testimony. I will first address those for nuclear thermal propulsion, and then I will review those for nuclear electric propulsion. Concerning nuclear thermal propulsion, our key findings were: first, we found that there are currently no nuclear reactor fuels that can provide the reactor temperatures to meet the required temperatures to meet the required performance or engine lifetime. The committee recommends that the characterization of reactor core materials, including fuels and moderators, begin immediately, as it is a fundamental risk to nuclear thermal propulsion technology. Second, we found that technology to store liquid hydrogen in space for the required mission durations does not exist. Our committee recommends that NASA develop high-capacity liquid hydrogen storage technology to meet the 3 to 4 year in-space storage requirement. Third, we found that subscale in-space testing of nuclear thermal propulsion systems cannot adequately address the baseline mission risks, and therefore full-scale integrated ground testing of the nuclear thermal system is required. Combining this full-scale ground testing with extensive modeling and simulation enables the use of the precursor cargo missions to Mars to meet the flight qualification requirements for the human mission, and eliminates the need for the precursor demonstration flights. Our committee recommends directly addressing these needs and adopting this flight qualification approach. Finally, our committee found that an aggressive program could develop a nuclear thermal propulsion system capable of executing the baseline mission in 2039, but that major challenges require near-term resolution. For nuclear electric propulsion, first, our committee found that developing a megawatt class nuclear electric propulsion system for the baseline mission will require increasing several subsystems power by orders of magnitude over available technology. Second, similar to nuclear thermal propulsion, our committee found that subscale in-space flight testing of nuclear electric propulsion systems cannot address the risks associated with the baseline mission system. But with sufficient modeling and simulation and ground testing, flight qualification requirements can be met by the cargo precursor missions. Additionally, nuclear electric propulsion may not require fully integrated ground testing. Modular subsystem tests at full power may be adequate. Our committee recommends directly addressing these needs and adopting this flight qualification approach. Finally, our committee found that due to low and intermittent investment over the past several decades, it is unclear if even an aggressive program would be able to develop a nuclear electric propulsion system capable of executing the baseline mission. To clarify, we're not saying that it cannot, but rather that we do not have the data now on which to base a good assessment. In summary, our committee found that either nuclear thermal propulsion or nuclear electric propulsion systems would provide substantial benefits to human Mars exploration missions, but that both systems have significant technical risk today. There is a need for significant investment in both systems before a data-driven selection can be made between the two. Thank you for the opportunity to testify. I'm happy to answer any questions the subcommittee may have.
Dr. Myers, thank you very much, and perfect timing. In the meantime, I'm in trouble because I neglected to recognize the chair of the full committee, the wonderful Congresswoman E.B. Johnson, for her opening statement. So, Dr. Lal, if you will allow me to pivot back to the chair of our committee, I recognize Congresswoman Johnson for her statement.
Thank you very much, Mr. Chairman. I really appreciate you holding this hearing. For decades, the space community has identified nuclear propulsion as a required and enabling technology for our human exploration goals. Even the best chemical propulsion capabilities of today mean long travel times to and from Mars and a long stay on the red planet for our astronaut crew. Space nuclear propulsion is a capability that can help address the safety of our astronauts by reducing their exposure to in-space radiation with shorter trips, reducing the length of time that the first crew stays on Mars, and would make the mission more feasible and likely to succeed. We've talked about this technology for a long time. It has been the subject of many studies by NASA, the Department of Defense, and the external advisory committees, including one led by retired Air Force Lieutenant General Tom Stafford in 1991. I want to know what we need to do to move from studies and talk to meaningful progress, whether it's R&D investment, developing safety standards, or building a STEM pipeline in nuclear expertise. I hope our expert witnesses can identify the necessary actions for advancing space nuclear propulsion and doing so safely. This capability will help our nation lead the inspiring and ambitious effort of sending humans to Mars. Further, it will keep the United States and our industry partners at the cutting edge of nuclear research, development, and applications. I look forward to the hearing from my expert witnesses this morning on the state of technology and what we need to do to move it forward. I thank you and yield back.
Thank you, Chairwoman Johnson, very much. I now recognize Dr. Lal for your opening statement. Dr. Lal, you are muted at the moment.
One second. I saw someone be muted.
Now we can hear you now.
Okay. Good morning, Chairman Baier, Chairwoman Johnson, Ranking Member Babin, and distinguished members of the subcommittee. It is an honor to again appear before Congress, this time on behalf of NASA, to talk about nuclear propulsion. Serving under Administrator Nelson and Deputy Administrator Milroy at NASA has been a dream come true for me. I hope I can convey to the committee the excitement the whole NASA team feels about the future of exploration, a future that assures continued American leadership throughout the solar system and beyond. As you know, under the Artemis program, NASA is endeavoring to return humans to the moon, but our goals don't stop there. Far from it. With the direction from Congress to expand human presence into the solar system, our eyes are on Mars and beyond Mars. If we want to explore the cosmos with humans and with robots, we need to develop mass efficient, high energy solutions that can power space vehicles, operate in harsh radiation environments, and increase mission flexibility. Nuclear fission systems can provide such solutions, delivering the high power levels needed to conduct exciting activities on the surface of the moon, reduce trip time of crewed missions to Mars, and carry large payloads with expanded maneuverability for robotic missions into space. Dr. Myers has already introduced nuclear electric and nuclear thermal propulsion systems. When combined with a chemical stage, an NEP, nuclear electric propulsion system, can provide fast transit to Mars. A shorter trip, as many of you have mentioned, would reduce crew exposure both to harmful galactic and cosmic radiation and to a reduced gravity environment. NEP reactors can also provide extensibility to higher power surface reactors and are considered the lowest mass solution for a fast transit to Mars. An NTP, nuclear thermal propulsion system, works differently, but can similarly enable a smaller and more versatile transport along with faster trip times. The ability of an NTP system to generate high thrust on demand could provide greater mission flexibility, including mission abort and return to Earth options if vital crew systems are not functioning properly. As with NEP chemical systems, the shorter trip enabled by NTP would reduce crew time and reduce gravity and space radiation. As Dr. Meyer said, both technologies are nascent and face steep developmental challenges. The National Academies study has concluded that the best path forward is to execute early dual path technology investments for both NEP and NTP and make more informed decisions in the next few years. To date, NASA has prioritized nuclear funding for fission surface power, which is a key capability for both lunar and Martian surface mission needs. Congress continues to signal through annual appropriations that NTP is a priority. As such, NASA's development in FY21 and prior years has focused on NTP. NASA's Space Technology Mission Directorate has been leading both surface power and propulsion activities. We are working with DoD and DOE to procure low-enriched uranium fuels from American industry. We recently funded 3 American companies to develop space-capable reactor designs. NASA is also sharing its space expertise, our space nuclear expertise, to support DARPA on their NTP flight demonstration, which is planned for the mid-2020s. Nuclear power systems for use on the moon could be developed within the decade. Nuclear propulsion capabilities will cost more and take longer. Indeed, realizing these capabilities would require sustained commitment and substantial investment over the next 10 to 20 years. It would demand working in lockstep with other government agencies, industry, and academia to ensure cost sharing and innovative development of systems. Let me conclude today by reiterating that nuclear power and propulsion applications in space are key to enhancing US leadership in space. Strategic competitors to the United States recognize this edge and are investing in fission systems themselves to fulfill their own ambitions. Development of space nuclear systems will also advance the state of the art for smaller and safer terrestrial nuclear power plants, helping to reduce greenhouse gas emissions. NASA's discovery of everything that we do is fueled by persistence to solve hard problems worth solving. The decisions we make now will have ramifications for centuries. Doing great things when others cannot is the definition of what it means to be a leader. No one has said it better than President Kennedy. We do these things not because they are easy, but because they are hard. Thank you for the opportunity to testify. We look forward to working together on doing great and hard things. And I look forward to your questions.
Thank you, Dr. Lal, very much. It does sound like NTP and NEP will be hard. So let's move on to our leader from the FFRDC, the Aerospace Corporation, Mr. Meholic. The floor is yours.
Thank you. Chairman Baier, Ranking Member Babin, and members of the committee, thank you for inviting me to join this discussion on behalf of the Aerospace Corporation. It is my honor and pleasure to testify on this exciting topic that has received more interest in the past few years than in the last half century. During my 20 years at Aerospace, supporting technology programs from the Air Force, Space Force, DARPA, NASA, and other agencies, I've served as a subject matter expert or project leader evaluating the design, development, and operation of space launch systems, as well as for advanced emerging propulsion technologies. In my current role, I am the technical coordinator, for most of the aerospace activities supporting cross-agency projects associated with fission-based space nuclear propulsion and power, or SNPP for short. There are 3 main points I would like to make to the committee regarding fission-based SNPP. My first point is that SNPP could offer enhanced mission capabilities. During the NOVA program 50 years ago, nuclear thermal propulsion, or NTP, engines demonstrated twice or more the cycle efficiency of traditional high-thrust chemical rocket engines. This means an NTP system can deliver the same amount of total propulsive energy, thrust, and acceleration to the spacecraft as a chemical system, but with roughly half as much onboard propellant. So for a given total vehicle mass, an NTP spacecraft can carry more payload mass than its chemical counterpart, or in other words, more science for less propellant. With electrical power, a space nuclear electric system would offer long-term, continuous megawatt-class electrical power that would be insensitive to line of sight or distance from the sun. If coupled to an electric propulsion system, otherwise known as nuclear electric propulsion, low-level, ultra-efficient thrusts could be produced continuously for perhaps months, depending on the mission. In short, SNPP could enable military and civil missions or capabilities not practically achievable using traditional means, and its adoption may therefore bolster US space national security and leadership. My second point is that SNPP technology maturation would benefit from the government-funded or a government-funded, government-led collaboration with industry and academia. In order to realize the potential benefits of SNPP, there are a number of technical, operational, and implementation challenges that must be addressed. Uranium fuel form development, materials technology, system modeling, test and integration, and a whole host of other aspects are at the hearts of current government and industry projects that are closely engaged with academic research. But due to the uncertainty for SNPP customers and missions, these projects are always concerned with funding, objectives, personnel, capability development, and a variety of other things. A series of multi-year government-funded, government-led efforts built upon SNPP maturation plans and dedicated to addressing these challenges would greatly benefit technology development and risk reduction to allow for timely implementation. Potential opportunities exist now to mature and advance space nuclear technology, which would establish the US as a world leader in such systems. My third and final point is that US regulations and policies for space nuclear systems should be tailored for SNPP. Today, policies and regulations for space nuclear material are centered around the uses of plutonium and other materials inside of radioisotope thermoelectric generators, or RTGs, which have been commonly used for sub-kilowatt levels of power for deep space missions. RTGs are always radioactive, and so the policies introduce strict compliance guidelines to ensure the safety and security of personnel in the environment. Fission-based SNPP reactors, in contrast, emit negligible levels of radioactivity until commanded to activate in space, thus significantly reducing safety concerns. 50 years of technological advancements in nuclear materials and science have further reduced the risk to public safety and are essential to the reactors being envisioned today. Therefore, regulations written for RTGs may be unnecessarily restrictive for SNPP development, ground test, launch, and in-space operations. Consideration of fission-based systems into policy and regulatory languages where the government could have a profound, near-term positive influence to inform technology maturation and could help more rapidly establish US capability and leadership in this area. In closing, space nuclear propulsion and power has advanced its viability and credibility well beyond concepts and analytical studies to the point of planned test programs, ground and/or flight demonstrations, and long-term technology maturation efforts. Both government and industry are beginning to re-examine potential capabilities of SNPP as feasible options for unique science, exploration, and national security missions. These heightened interests are supported by a robust nuclear industry base, heritage programs, technology advancements, and interests of committees like this that may be highly influential towards developing near-term national capabilities. My sincerest thanks to this committee for holding this hearing and for your generous attention. I look forward to your questions.
Thank you, Mr. Meholic, very much. We'll now hear from Mr. French. Mr. French, the floor is yours.
Thank you, Chairman Byer. Chairman Byer, Chairwoman Johnson, Ranking Member Babin, and members of the subcommittee, thank you for the opportunity to testify today. The Aerospace Industries Association represents the largest and most diverse coalition of aerospace companies in the United States. We represent over 300 companies across the aerospace supply chain, from family-owned small businesses to large system integrators, and from publicly traded to privately held to venture-funded startup companies. This morning, I'll focus on 3 policy areas important to accelerating space nuclear propulsion. As Chairwoman Johnson said in her opening remarks, how we move from study to action. I'll focus in particular on those areas where the subcommittee is and continue to be a key enabler. I'll begin with recent changes in executive branch policy. Nuclear systems have been a part of America's space program since the beginning of the space age. The process for approving the launch of nuclear systems was recently updated to reflect this legacy. Under this change, the launch of a nuclear thermal propulsion flight demonstration would likely be considered a mission under the approval authority of the NASA administrator. This would not change the host of safety and regulatory requirements for the launch, but would focus and expedite the overall process. Another recent executive branch policy development was the issuance of Space Policy Directive 6, or SPD 6. SPD 6 directs the whole of government approach to advance nuclear space systems development and provides a roadmap with specific agency roles and responsibilities. Maintaining interagency coordination and defined agency milestones are important to policies for accelerating nuclear propulsion development. This takes us to the first enabling action. Affirming these executive branch policy updates is a key action the subcommittee can take as it considers future authorizing activities. Let me turn next to funding. Stable, sufficient funding is critical to accelerating the development of nuclear propulsion technology. Here, Congress deserves praise. Congress has consistently funded the NASA budget on a bipartisan, bicameral basis, with 8 consecutive years of appropriation increases. That number is 9 consecutive years if you count the pending FY22 House and Senate appropriation marks. Importantly, this support has been balanced across the NASA portfolio, supporting aeronautics, education, exploration, science, and space technology. Within these consistent, balanced appropriations, Congress has funded nuclear thermal propulsion on a multi-year basis. Congress's funding aligns directly with the timelines established in NASA's technology roadmaps. Congress has also recognized the importance of a flight demonstration to move this capability forward, and has consistently included direction for a nuclear thermal propulsion flight test along with its funding. The President's budget request has not aligned as directly with the technology roadmaps. Finalizing the FY22 marks and test direction and continued support in FY23 and beyond is a second key policy action Congress can take to accelerate the development of this technology. Finally, and of particular relevance to the subcommittee, is a NASA reauthorization. In the previous Congress, this subcommittee passed language directing the NASA administrator to, quote, develop a plan, including a cost estimate, to achieve an in-space flight test of a nuclear thermal propulsion system within 10 years of the enactment of this act. The Senate passed NASA authorization included similar direction with an accelerated flight demonstration timeline. Passing a NASA reauthorization is the third key policy action Congress can take to accelerate the development of this technology. It would also provide important direction across the NASA portfolio. The subcommittee should again consider authorizing nuclear thermal propulsion activities, establishing a flight demonstration date, and endorsing accelerated partnership and coordination between NASA, the Department of Energy, the national security agencies, and industry on nuclear thermal propulsion development. In sum, Congress and the subcommittee have been key enablers to accelerating the development of this technology and can continue to do so by finalizing FY22 funding and direction, providing direction in a NASA reauthorization, and continuing its support in FY23 and beyond. Thank you for the opportunity to testify today, and I look forward to answering any questions.
Mr. French, thank you very much. And now finally, we'll hear from Dr. Franklin Chang-Diaz. Dr. Chang-Diaz, the floor is yours.
Thank you, Mr. Chairman and Chairwoman Johnson, Ranking Member Babin, and distinguished members of the subcommittee. I am very honored to be called to testify before you on this important topic for our nation and for our civilization. Space travel beckons humanity even more today than I think it did in the 60s, and not to abandon our planet, but to care for it, to preserve it, to protect it, by providing an opportunity for all humans to thrive and prosper in a universe of possibilities. So to do that, we must secure a safe and robust and a fast means of transportation. And nuclear power offers us that opportunity, but there is homework to be done. In rocket propulsion, the faster the rocket exhaust is, the better the rocket. To make the exhaust fast, we have to make it hot. The best chemical rocket runs at thousands of degrees and has an exhaust velocity of about 4,500 meters per second. Nuclear rockets come in two flavors, nuclear thermal and nuclear electric. The goal is the same for both, to heat the propellant to high temperature and expel it. In nuclear thermal, the reactor is a contact heater to heat hydrogen and expel it. In nuclear thermal rockets, you could increase the exhaust velocity to about 9,000 meters per second, but higher temperatures are constrained by materials limitations. In the nuclear electric rocket, temperatures of millions of degrees are accessible because at those temperatures, the exhaust is an electrically conducting plasma, a soup of charged particles which responds well to electric and magnetic fields. In the Vasmer engine, for example, we take advantage of that feature by using a magnetic field to hold and guide the plasma, keeping it away from any material surface as we heat it. The heating is done with electromagnetic waves, so nothing physical touches the plasma. In these devices, exhaust velocities of 30,000 to 50,000 meters per second are measured, an order of magnitude greater than chemical rockets, and higher velocities are technologically feasible. The nuclear reactor here is not a heater, but is an electrical power plant. And the big challenge is to develop powerful, compact, and efficient nuclear electric power source and an electric rocket capable of handling all that power. This is the homework. We must do it if we want to lead. The potential payoff is extraordinary. For example, with a power and propulsion package weighing about 3 to 4 kilograms per kilowatt and operating about 20 to 30 megawatts, human Mars transits of less than 3 months would be possible. Nuclear electric also extends the departure and return windows for Mars from days to weeks and provides a variety of in-flight abort options if they were needed. So in space, power is life. And with nuclear electric, the reactor also provides an abundant supply of electrical power for the ship. The nation has made investments in nuclear thermal. We need to invigorate the nuclear electric option as well. It is the right time. Our own Vasimer engine recently achieved a major milestone with an 88-hour high-power continuous endurance test last July, a project supported by private investors and NASA. Other high-power technologies are also poised for development. It is also the right time as nuclear electric draws on advances in fusion energy innovation, now also with private sector investment, and advances in power electronics for electric vehicles. To lead in space propulsion, we must invest in disruptive innovation. Mr. Chairman, members of the subcommittee, as our nation moves to explore deep space with humans, we must be able to travel fast to reduce the debilitating effects of space on the human body, to reduce the burden of consumables, life support, to be less constrained by the planetary alignments and tight launch windows, and to expand our capability to recover from unforeseen contingencies en route. In short, this is the problem punch list we need to solve to give our astronauts a fighting chance in deep space. The development of high-power nuclear electric propulsion is critical to checking those boxes and to meeting our nation's goal in space. So thank you, and I'm happy to take your questions.
Thank you, Dr. Chang-Diaz. That concludes our presentations from our 5 expert witnesses. We'll begin the round of questions. I get to go first by virtue of the history right now. So Dr. Chang-Diaz, this Vasimer engine that you worked on, so you have a PhD in plasma physics?
That's correct.
And it seems like you're using tokamak type ideas, electromagnetic fields to hold the high plasma in, very parallel to what they're doing in the fusion research here on Earth.
You're right.
When you talk about 30,000 to 50,000 meters per second, it is obviously much faster than the 9,000 meters per second that an NTP would give you. But is that still fast enough to get there in a reasonable amount of time?
It is if you run the engine long enough. These electric rockets are low thrust but continuous thrust. So you are accelerating all the time. And so what you end up doing is you go halfway to Mars, and then you start turning around and decelerating so that you don't overshoot the planet. But yes, in the end, you go faster than with a nuclear thermal or even a chemical rocket.
Thank you. Mr. French, one of the most obvious questions is, if we can't get to Mars using the traditional chemical stuff, and we have to turn to some type of nuclear propulsion, why the zero request in the president's budget for this? And why so little? If we look at your chart about FY 17, 18, 19, 20, no specific funding at all, 100 million in 2021 and then 0 in 2022. What's been missing from NASA's request or the president's request?
I could jump in with that, Mike, if you'd like. So,
or both, please.
Okay.
Thank you, Mr. Chairman. And so I can't speak to what happened within NASA in FY22. I will say from my experience, both at the White House and NASA in prior administrations, what I often encountered is that NASA would have important technology needs and develop technology roadmaps. And sometimes the budget for those requests didn't quite make it through the full budget process at the end of the day. And so often, sometimes you could find something where a technology need may not necessarily at the end of the day be reflected in the final PBR. That's in general. I really have to turn to NASA to explain what occurred, in FY22. But I'll certainly say, can't understate what the Congress has done so consistently here with its support in recognizing the need of this technology.
Hooray for Congress, but Dr. Law, where's NASA on this?
So thanks, Mike. So nuclear propulsion, as we just discussed, is critical to America's future in space. There is no doubt. However, with the limited resources available to NASA for tech development efforts, our priority has been to focus on surface power, fission surface power first, which is not only a near-term requirement for long-duration surface missions on the moon, but has extensibility to the nuclear electric propulsion, and that's an important thing to point out. The FY22 budget does include many technologies that apply to propulsion systems. One of the most important ones is cryogenic fluid management systems, which are critical for propulsion, for long-term storage of hydrogen and other volatiles in space, and not just for in space, but also on the surface of Moon, Mars, and other bodies. We are also continuing work in terms of the budget on space-rated power conversion systems, LEU, low-enriched uranium moderator materials, and lighter weight radiation shielding, all of which apply to propulsion. NASA, of course, looks forward to working with Congress and the administration to develop a balanced, a schedule-driven investment strategy for our nuclear portfolio.
Thank you, Dr. Law. Mr. Meholic, you really talked very much about tailoring regulations to the SNPP, and you compared it to the RTGs, the plutonium radioactive. Is this parallel to the efforts on Earth to distinguish fusion energy from fission energy? Getting the fundamental difference that these are very different power systems with very different dangers and advantages.
Yeah, absolutely. The RTGs, as I mentioned, are always on as far as, even from their manufacturer, they have to be carefully handled in proper facilities and so forth. And even during launch, the RTG device is actually one of the last things to be loaded onto the launch vehicle before all personnel leave the pad. With a nuclear fission system, though, that is not the case, right? These are basically just giant hunks of metal with some uranium in it for all practical purposes. And, it is not critical in any way, shape, form, or manner. It can be handled safely and so forth. What I meant by the policies, to kind of touch on that a little bit more, is there is, the presidential memorandum number 20 that talks about launch approval for these types of reactors. But there's also other policies associated with DOE and DOT on perhaps the testing of these types of things. A number of the folks here in the testimony mentioned about ground test, the need for ground test, the value of ground test. But there are really no current regulations that would allow that in such a way that would not be prohibitive or take years to try to overcome from environmental studies and things like that. So the point I was trying to make on that was to be able to streamline that process and really look at the safety aspects of these new types of reactors as opposed to 50 years ago, and determine if the policies and regulations in place that would govern ground test and operation may have to be tailored in some way. And granted, RTGs and that type of testing is a different realm, as if we were to try to test a nuclear thermal propulsion system in the open air like they did for NERVA. So, NASA right now has a dedicated task to look at ground test options, facilities, and so forth for one of their space nuclear propulsion projects, nuclear thermal propulsion centric right now. And those types of policies need to be looked at a little bit deeper.
Thank you.
Thank you very much for the question, sir.
Yeah. Thank you, Mr. Meholic. And let me now recognize the ranking member of our Space Subcommittee, Dr. Babin of Texas.
Okay. Thank you, Mr. Chairman. I appreciate it. Dr. Law, in May, China became the only non-US country to successfully deploy a rover on the surface of Mars. And shortly afterwards, China announced that it intends to conduct crewed missions to Mars in 2033. The head of the China Academy of Launch Vehicle Technology indicated at the time that to shorten the travel time, spacecraft would have to tap energy released from nuclear reactions in the form of heat and electricity, in addition to traditional chemical propellants. What insight do we have, and please keep this as short and abbreviated as you possibly can. What insight do we have into China's current capabilities regarding space nuclear propulsion? How much are they spending? Are their schedules realistic? Are they focusing on NEP or NTP? And if they're focused on both, what technology is farther along? And could they develop and deploy space nuclear propulsion before we do?
Thank you, Ranking Member Babin. Our strategic competitors, including China, are indeed aggressively investing in a wide range of space technologies, including nuclear power and propulsion, to fulfill their ambitions for sustained human lunar presence, as well as Martian and deep space science missions. So there's no question that there is investment at a level that we do not understand. Data is hard to come by, and I can take some of your specific questions for the record and come back to you. On space nuclear, we have seen long-term planning on part of China for human missions using nuclear systems in the late 2030s, similar to our plans. The United States needs to move at a fast pace to stay competitive and to remain a leader in the global space community.
Brian, you're
muted yourself.
Yeah.
There we go. Thank you. I'm sorry. Extensibility, this is for Dr. Lau as well. Extensibility is the concept that technologies developed in the near term will be useful for the future exploration as well. Extensibility prevents the development of dead-end capabilities. Nuclear surface power will be required for crewed mission operations and missions on the moon. Surface power generation would presumably be extensible to nuclear electric propulsion development for a mission to Mars as well. NTP is already being developed by the Department of Defense to meet their needs, and Congress has appropriated hundreds of millions of dollars for NTP over several years. Referring to a mission to Mars, the Academy report stated, if NASA plans to apply nuclear electric propulsion or NEP technology to a 2039 launch of the baseline mission, NASA should immediately accelerate NEP technology development. How is NASA supporting the development of NEP, which is critical, in my opinion?
So we are, as per congressional direction, we are focusing our effort on NTP. However, as you noted, NEP is a critical capability we must achieve. Our investment in surface power does have extensibility to NEP, although I should point out that depending on the wattage of the surface power, that NEP may be more applicable for deep space science missions, which are extremely important for us. And over time, they can go up to the power levels that would be required for an NEP human mission. So, we are looking at about 10 kilowatts to 40 kilowatt like systems for surface power for the moment. We need to be looking at higher levels. For a human mission to Mars, we should be looking at that NEP system is more like 2 megawatts. So there's a lot of extensibility that needs to happen from surface power to NEP.
Gotcha. Okay. Well, thank you. Thank you so much. And real quickly, Dr. Myers, there have been exceptional advancements in high power electric propulsion, or EP, accelerated by recent investment from the private sector, such as in the NASA Next Step public-private partnerships that led to the recent 88-hour endurance test of a VASMR test engine by a constituent of mine. Additionally, who we are hearing from today. Additionally, electric propulsion innovation benefits from fusion energy development, now also accelerating with private investment, and the great advancements in power electronics for transportation and industry electrification. Yet high power electric propulsion development has suffered from low and intermittent investment over many decades. The National Academy of Sciences panel recommended that the U.S. must accelerate a robust and sustained program to develop high power electric propulsion thrusters needed to maintain and advance our leadership in space propulsion. How should NASA prioritize investments in both incremental innovations, such as the Hall effect thruster, and disruptive innovations, such as the VASMR engine?
I think at this point, thank you for the question. And
Yes, sir.
at this point, our committee recommended a balanced approach focused on leveraging the capabilities of well-established technologies, while at the same time maintaining a portion of the investment in the breakthrough technologies. Having a balanced portfolio of technology investments is the best way to mitigate program risk. And at the same time, you really want to leverage, we found that you really want to leverage the capabilities, the established capabilities, and frankly, the engineering know-how and the deep understanding on the Hall thrusters and the MPD thrusters. For example, the lithium MPD thruster has actually fired for 500 hours at 500 kilowatts. So that's, you know, we commend the progress. We were excited to read about the progress that Vasimir had demonstrated, that Franklin and his team have demonstrated excellent progress. And that certainly should continue. At this point, we do not have enough data to make a good decision between the different technologies for this very high power. Nobody has invested much money in the very high power systems. And we need a more sustained investment in those very high power systems.
Thank you, Dr. Myers, and thank you, Dr. Babin.
Thank you very much. I had another question, but I see that we're out of time, Mr. Chairman. Thank you.
Great. Thank you.
Dr.
Thank you
Babin.
very much.
Yes,
Dr.
sir.
Babin, may I interject for a second, sir?
Sure.
Building off of Dr. Myers' comments, and thank you for allowing this. You know, I agree with his points 100%. I read the National Academies report, and they identified also, as is well known, the number of critical subsystems associated with nuclear electric power, right? The electric power thruster, as was pointed out, is a technology that's decades old. All right, there's advancements that may need to accommodate these, to accommodate these types of Mars missions. But these other subsystems, like the power generation system, the actual reactor, the cooling and the heat rejection, and all the other subsystems are absolutely critical in order to provide the power to those electric thrusters. And those actually just come into, as what I described in my testimony, is just the space nuclear power part. Those also need dedicated development programs that have yet to be realized in any great form, especially for the power and the durations expected for these highly ambitious Mars missions.
Let's move on, because we have lots of people in the queue.
All right. I really
Hopefully
want
these
to
questions
hear
will
what
come.
Dr. Chang-Diaz had to say about it, but looks like.
Well, and Brian, hang in, we can do a second round too.
Okay. All right,
So
thanks.
now let me recognize the chair of the full committee, Congresswoman Johnson.
Well, thank you very much. Dr. Myers, in the National Academies report, your panel found that NASA needs to accelerate its development programs in nuclear propulsion, whether nuclear thermal or nuclear electric, in order to meet the requirements for a Mars mission in the 2030s. Is achieving this capability primarily a question of adequate resources, or are there other factors?
I would say that thank you for the question. And I would say that the primary factor is adequate resources. As was noted, there has been some significant investment over the past 8 years in nuclear thermal propulsion, but there has not been a commensurate investment in nuclear electric propulsion. And so we found that we do not have the information, the data which are needed in order to make informed decisions about all of those subsystems that Mr. Meholic just mentioned, for example. There are, however, some very fundamental questions about both nuclear thermal and nuclear electric. The risk associated with achieving the temperatures and lifetimes in the reactor fuels for nuclear thermal is a fundamental materials challenge that we think is quite likely solvable, which is why we came to the conclusion that it was possible to meet the time frame for the baseline mission, but we're not 100% sure. There's real technical risk there and some fundamental materials work that needs to happen on the reactor fuels for nuclear thermal. Nuclear electric is more of a scaling question. It does not have exactly the same kind. It has very different challenges, in fact. And so I would say it's primarily a resource question, but there are some fundamental materials, some fundamental science questions that need to be addressed immediately, as we say in the report, in order to really get to the point where we can be sure.
Well, thank you. Now, the National Academies report that you co-chaired, of course, noted challenges in the STEM education and workforce pipeline for advancing space nuclear propulsion. The report identified 3 key challenges: a lack of gender and ethnic diversity, competition for talent, and export control and classification regulations. How do these challenges affect the space nuclear propulsion sector, and what needs to happen to address these challenges?
Thank you for that. That's an excellent question, and it's one of that's very relevant in today's society. I would say that the resources need to be put on these technologies in order to attract the students and set up the pipeline that is needed to get the students excited and interested. And we need the programs at the universities, and then we need the programs even further down to get people excited about all the different aspects of space exploration and space nuclear propulsion. We got to fill that pipeline with smart kids who are excited, and a diverse population of kids. And we can't do that without resources. So we really need a balanced portfolio of work to support a broad engagement of students across the nation. I hope that answered your question. I apologize if I missed part of it.
Yeah, it's a challenge. Thank you, Mr. Chairman. I yield back.
Thank you, Madam Chair, very much. Now I recognize the Congressman from Cape Canaveral, Mr. Posey.
Thank you, Chairman Byer, for holding this hearing on space nuclear propulsion for enabling deep space exploration. Mr. French, in your written testimony, you mentioned policy improvements have already taken place for launching nuclear payloads with the National Security Presidential Memorandum 20 in 2019. Why was the National Security Presidential Memorandum 20 so important?
Thank you, sir. What it did is it updated a policy that had essentially been unchanged since the late 1970s. And in that time, we've certainly had quite a bit of experience launching nuclear space systems. What it does is it's very important that it doesn't change the overall safety and regulatory requirements that would have to take place to approve a launch. But what it does is it shifts the final approval for certain launches, including likely what would be a nuclear thermal propulsion launch, from being led by a presidential approval to one by the NASA administrator. Now, again, it doesn't change the safety and overall regulatory requirements, but what that would do is, if in NASA mission, it would allow more focus in driving the process and ensuring that all the gates were met in a timely fashion. And so that's the primary positive thing there.
Okay,
Could I add to that response?
Sure.
I would just like to add to that everything Mike said was absolutely accurate, but I think one big innovation in the presidential memorandum was that the analyses are based on the characteristics of the system, the levels of the potential hazard, and national security considerations, and all of those are made quantitative. So the process that existed before since the 1970s was very open to interpretation and a lot of discussion, and it was just very expensive because there was no sort of level of safety to which you were trying to aim for. With this update, there are quantified risks that we aim to address, and that's a good thing all around. That makes safety better, it makes costs lower, and it increases the speed at which we can achieve our objectives.
Thank you. Mr. French, how would that policy change be an important enabler for thermal propulsion systems that would be needed for deep space?
Yes, sir. So under the as Dr. Law talked about, there's 3 different tiers under the new policy. And as the policy is designed, a flight demonstration of nuclear thermal propulsion system would fall likely under tier 2, which would gain the benefits that Dr. Law just discussed.
Okay. And is there anything Congress could do to expand upon the memorandum to keep America the preeminent leader?
Yes, sir. I'd say that on the policy side, affirming these positive improvements through authorization activity would be very important, as well as affirming the nuclear the language that the subcommittee considered last Congress would be a very positive step.
Yeah, thank you. Mr. Meholic, whenever a launch includes a payload with a nuclear reactor, there's a huge process to safeguard threats to life and the environment. In your written testimony, you stated fission-based SMPP, space nuclear propulsion and power systems, are manufactured and launched in the off state that would dramatically reduce any threats to the environment or life. Can you give us an example of how that might protect lives, let's say on the Space Coast, for example?
Sure. Thank you for the question. Yeah. So as I mentioned in my earlier words here, RTGs are always hot, given that the nature of plutonium, right? It's always radiating. There always has to be shielding and so forth. And if there was a launch accident, that material inside of that reactor would still remain in that active state, and would fall down into the oceans and onto the land, depending on where the accident occurs, and potentially have to get analysis and assessed for what kind of damage would be produced. With a uranium-based nuclear fission system, the uranium is actually not fissioning. It is very, very negligibly radioactive at the time during manufacture, during the fuel formation, during its insertion into the reactor. And it basically is a giant chunk of metal that weighs several tons, not unlike a normal spacecraft. So if an accident were to occur, this metal would come down, possibly as a single piece, but unless there is some form or command or significant consequence that would cause it to go critical, it would otherwise remain as a giant chunk of metal and just splash down into the ocean with no results. But obviously, the analysis would have to be done for the criticality analysis and everything that accompanies any kind of a normal launch when you're dealing with this type of thing. So that would still continue.
Thank you, Mr. Chairman. I yield.
Thank you, Mr. Posey, very much. Now I recognize the Congressman from Mars, Mr. Perlmutter.
Thank you, Mr. Chairman. I appreciate that. Just a couple thoughts. The good news and bad news for us in Congress is we have one of the top nuclear physicists in the country on this panel, Dr. Bill Foster. So the good news is he can interpret all of the things you all are talking about, nuclear fission and nuclear fusion and plasma containment and all that stuff. The bad news is we have to listen to that all the time too. So what I want to talk about is every one of you has addressed the need for stable and sufficient resources. And that's really what Congress must and can. That's our responsibility as the board of directors here sending out a mission. So let me begin with just assume that between the Defense Department, the intelligence agencies, the Department of Energy, and NASA, the budget is sufficient, and you know where I'm going with this, to get our astronauts to Mars by 2033. Dr. Myers, your report is pretty sobering, quite frankly, for an exuberant guy like me, and maybe I'm being unrealistic. But are there any fundamental scientific limitations to us being able to get to Mars by 2033 if you had sufficient resources? I mean, does it just take that much time to do the kinds of research and testing that's necessary?
Yeah, unfortunately, it likely does. There are some fundamental, as I mentioned earlier, the materials challenges for nuclear thermal propulsion may really limit its capabilities. But when you look at the overall mission architecture and the propellant, the launches that you need, the precursor cargo missions, just the normal Mars orbital dynamics, right? The synodic cycle. When you look at all of that and you ask about the technology development requirements from where we are today to launching a crewed mission, we saw that as a tremendous challenge and possibly unobtainable, likely unobtainable by 2033.
All right, so I guess I'm the kind of guy that thinks that between the scientific community, the engineering community, the technical community, we can do that. I know you guys can do it. And the reason that we set 2033, or I've become so obsessed with it, is 4 years ago or 5 years ago, we had a couple senior people from NASA, I think it was probably 2016, 2017, saying 2033, the orbital mechanics is good. That gives us a 15-year lead time. And yeah, we can do it. So Dr. Lal, can we do it?
So I agreed with everything Dr. Myers said, but I would like to add some other things to it. So deep space transport is just one piece of getting to Mars. There's also the entry, descent, and landing, which is very, very difficult, and we have not invested much in it at all. We've landed small rovers and landers, which is not at all like human landers, right? So that's a second piece. The third piece is environmental control. I mean, we have to take these, our best humans, the best Americans are heroes, in these vessels, and we need to make sure that the environmental control and life support systems can keep them alive for 2 to 3 years. I mean, nuclear cuts the travel time by maybe a year, but it's still about 2 years. And the last but not least piece is radiation protection. So, there's huge amounts of galactic and cosmic radiation the astronauts would be exposed to, and we need to understand the impact of the radiation on the human body. So transportation is just one element. There's all these other elements as well, and funding everything together while we are also interested in having.
Okay, I know it's going to be a challenge. I've been listening to this for 5 years, and I know you people can do it. So I'm going to turn to Mr. Meholic right now, and I wanted to give Dr. Chang-Diaz a chance to, and I wanted to talk about SPD 6, but Mr. Meholic.
Yes, I also wanted to thank you very much for the question. As far as resources go, there's also the resources of launch acquisition and launch vehicles to get to orbit to put these types of things together. One area that's not touched on very much is the advancements that are needed in on-orbit and automated assembly in space of these types of large spacecraft, regardless of what the propulsion system is, and how to launch those systems and the availability of those systems and qualification of those systems by the time frame you're talking about, sir. That's all. Thank you.
So I'd just like to conclude and wrap that up by saying, when the committee looked at all of those issues that Dr. Lal and Mr. Meholic mentioned, that's why we came to the conclusion that we did.
All right. Well, I'm going to push you because I know you can do it.
Excellent. We look forward to having the resources to do our best.
And Congressman Perlmutter, unless the committee overrules me, we're going to try to do a second round too. So hang in there. Now let me recognize the original Daniel Webster from Florida. Congressman Webster, the floor is yours.
Thank you for putting this on, Chairman, and really appreciated. This is technologically challenging for all of us, I guess, especially me. I was wondering, is there any thought to where the launch point should be? Should it be on the Earth or should it be external to the Earth? And I'm not sure who would be the right person to answer that question.
I'm happy to jump in, and then I'm sure others of our witnesses have good things to say. I would say that the bottom line is that right now, everything starts on the surface of the Earth. So we have to get to space, the departure, and then actually, as Mr. Meholic mentioned earlier, there's an assembly point in Earth orbit where you bring all of those resources together. And then the mission to Mars will depart from Earth orbit. So you launch from Earth into orbit, do a vehicle assembly process in orbit,
So
and
the
then go to
initial
Mars.
launch is a whole bunch of stuff with them. It's not, you're only taking people and parts and all kinds of other things, and then it's assembled in space.
Yes. Yeah, it's assembled in orbit, in space, and then it goes to Mars from that point.
Is there I mean, is it a deep orbit or a shallow orbit or
Frankly, that has not been finalized yet. We in fact looked at two options. One, and when we had presentations, we had lots of people providing us input, but there are options to do a low Earth orbit assembly or a high Earth orbit assembly, or frankly, even assemble around the moon. NASA has done some mission architectures using lunar orbit as an assembly stage point. So we've looked at all of those, or the community has looked at all of those options. And one of the findings of our committee was that we really need an apples to apples comparison of these different mission what we call mission architecture options, different ways of performing these missions in order to finalize one.
So does that affect the timing? We were talking about particular years we're looking at or whatever. Does that change the timing or the of the actual distance after you get into space? Does that really matter?
It can change the amount of time that the astronauts are in space, but it doesn't change it dramatically, because the moon is bound to the Earth, and so fundamentally the orbits are guided by the Earth's orbit and Mars's orbit, for example. So it can affect it somewhat, but it does not affect it fundamentally.
Is there any change, like if you're doing it in space, does that change the type of energy used to propel the ship to Mars?
No, it doesn't, because again, fundamentally you have to go from an Earth orbit, wherever you assemble in Earth orbit, be it even a lunar orbit, the moon orbits around the Earth, and so fundamentally it does not. It can have effects on it definitely does impact it some, but not dramatically. And other panelists, feel free to jump in.
I guess I would just add to that, if I might. The space station, low Earth orbit, is about 400 kilometers. Moon is 400,000 kilometers. Mars is 400 million kilometers. So being, in Earth orbit versus moon orbit really doesn't change a whole lot. And it's about the same time, regardless of where the assembly happens.
Thank you, Bob.
And if I may also, sir, the assembly of these types of spacecraft, regardless of what their propulsion is, if it's nuclear, electric, or nuclear thermal, is going to require perhaps dozens of launches, depending on the launch vehicle and how much each one of those rockets can carry to the assembly orbit, right? The further out you go away from Earth to assemble, the larger the launch vehicle you're going to need, depending on the mass that you're sending up, which could be several tons, right, of payload. So being able to do that, acquire the launch vehicles, get all the launch approvals, and send these things to the right orbits is critical. And I know the time is coming up.
Is there any way to start now doing that?
We really need to make some other decisions about technology approach. I think we need to make some fundamental progress on the technologies before we start the mission itself. So we do need to establish the infrastructure required to, at the technology level, and then the ground infrastructure and the in-space infrastructure before we can really start the mission, I would say.
Thank you very much. I yield back.
Well, sure. Now it's my honor to recognize Dr. Foster, who with Mr. Perlman and others, I thoroughly enjoy trying to keep up with the many different ideas that he has. Dr. Foster, floor is yours.
Okay, well, all right. Am I audible here?
Yes.
Okay. Well, actually, just to follow up on just the previous question, at what point, when you look at different assembly scenarios farther from Earth, what point does the radiation burden on whatever humans are assembling stuff become a driving factor? You know, is that turn into be a problem for example, lunar assembly?
The assembly would probably be primarily automated, as in we talk about autonomous rendezvous and docking, for example, and autonomous assembly. It would need to be added to the in-space time of the astronauts, but those astronauts doing the assembly would probably not be the ones actually going on to Mars. Okay. So there probably, you know, in that scenario, there would probably be a way to balance all of that and to end up again minimizing the radiation exposure of the,
well, the worst case for the ones that actually make the trip.
Exactly.
Yeah. And let's say, what is the best understanding of the performance hit that you take in the low enriched versus high enriched uranium? You know, both for nuclear thermal and for, you know, surface based power reactors. You know,
I'll go first and then Greg. So it turns out that at these power levels and at these either nuclear thermal or nuclear electric, there really isn't a significant power hit for highly enriched, for HALEU, for low enriched uranium. The scale, you can design the reactor to operate just as well with HALEU or HEU. It is a different reactor design. You have to design it differently, but there is essentially no.
So you're limited by thermal transfer from whatever fuel assemblies you have, and it doesn't matter what's inside, pretty much.
Pretty much.
And is there a difference?
At this scale, I'm sorry, yeah. Let me just finish by saying that at small scale, so for some of these, the systems that Dr. Lal was talking about for near-term surface fission power, there is much more of a penalty. So at 10 kilowatts, there is a significant penalty between the two. You can still build a HALEU reactor. It'll still work fine. It'll just be heavier than you want. But as you scale up in power, that penalty is dramatically reduced.
All right. And so the other effect that may be hard to quantify is the effect on mission cost. Just because the tremendous security, I'm sure most of you have been in a place that handles high enriched uranium. It's my understanding that the commercial enterprise interested in this are pretty much uninterested in high enriched uranium. Is that
is certainly what our committee was explicitly told, that if industry is going to do it, it must be HALEU. It must be the high assay low enriched uranium, not HEU. HEU is a killer for.
Yeah, and if I may, that plays directly into sort of the non-proliferation policies that the United States has with, you know, internationally is the use of HEU. And also to touch back on Mr. Meyer's points, and as correctly described, you know, the performance hit is minimal between HALEU and HEU. But there is a mass change, right? You know, there have been a number of studies that showed that if you use a HALEU type of reactor for the power levels and thrusts are described in space nuclear propulsion and power, the core and the actual reactor core may only be about 15 to 25% heavier for a HALEU system than for an HEU system. What that means to an overall spacecraft mass when you're talking 100 metric tons is very, very little, right? Is the change in weight there. So the performance of the engines, as Dr. Myers stated, is going to be about the same regardless of the core.
All right. And so the mission impact combined with the cost impact and the fact that you basically have to go to weapons labs to you know, to do an HEU design and to test it and everything else. So okay, that's interesting.
Could I add one more?
Yeah, the one corner that still made sense was the short-term low power surface reactors, which was a prototype that was tested a few years back. And what's the status of that? And what direction are we going in there?
So if I could take that question. So I just wanted to add another point to what Dr. Myers and Dr. Meholic said. Every single reactor effort we've had in this country in the last 50, 60, 70 years has been an HEU effort. So as we switch to HALU, which we have, we really cannot leverage a lot of those lessons. So we cannot say, oh, doing X would be easier because we did that in the 50s, because what we did in the 50s was with the system that's not really transferable. So I just wanted to make that point. But to your question on the status of Kilo Power, it was a zero power criticality test. It went very well. And since then, NASA has determined, and I can get you details by email, has determined to move from the HEU to a HALU system, and those designs are underway. NASA is currently looking at releasing an RFP, a solicitation for power reactor systems the end of this year, and it would be asking for a HALU design for surface power on the moon.
Thank you. All right, my time is up, but it looks like there's no reason to reconsider and look back on that decision at this point. Good. Okay, thank you. I yield back.
Thank you, Dr. Foster. Now recognize the Congresswoman from California, Representative Kim.
Oh, thank you very much, Chair. One of the recommendations in the Committee on Space Nuclear Propulsion Technologies report on space nuclear propulsion is for NASA to develop consistent figures of merit and technical expertise to allow for an objective comparison of the ability of NEP and NTP systems to meet requirements for a 2039 launch of the baseline mission. Dr. Lahr, I have a question for you. Has NASA officially adopted this recommendation and commenced a trade study to compare NEP and NTP systems? And if so, when can the committee expect the results of this study?
So Congresswoman, yes, NASA has accepted that recommendation. We are completing a study, and it is in review by external non-advocacy experts. The basic takeaway from the study I can summarize in 3 quick bullets. We found that both NTP and NEP chem systems have the potential to fulfill the mission requirements for a fast transit to Mars in the 2030s. However, as we've been discussing, it's a different set of challenges for both, with NEP advantage in the lower mass and fewer launch vehicles. Those are kind of the big picture takeaways, and we will make sure that once the report is reviewed and updated, we can get it to you.
Thank you, Dr. Lahr. Maybe to any panelists, I have a question for one or all of you. How are departments and agencies collaborating on SNPP systems? Are they conducting a regular technical exchanges among SNPP programs? Mr. Myers?
Yeah, I would say that yes, they are working very closely together to my knowledge. I'm not directly involved, but I have spoken to various people in the agencies, and they are actually directly engaging the Department of Energy, the Department of Defense, and NASA working very closely together. And probably Dr. Lahl will probably be able to speak directly to this.
I'd be happy to. So as Dr. Myers said, DARPA is developing an NTP flight demonstration that is representative of a high thrust system needed for national security cislunar near the moon operations. Of course, such a system would provide NASA with valuable knowledge in the area, including things like launch regulations, reactor and engine operations, and thrust control for future NASA and other missions. On this particular program, which is called DRACO, we have a memorandum of understanding in place. NASA's Marshall Space Flight Center is supporting this effort. At DOE, the Idaho National Lab is getting upgraded and could be used. And INL is also handling some of the early design contracts. Another part of DOD, we are SCO. I'm struggling with what SCO stands for. It'll come to me. We are working together. So they are developing a ground-based reactor for forward bases. And we are working with them on fuel production because they're also looking at HALU. But they're not the identical fuel, but similar enough that we can collaborate. And again, we have a MOU in place with the Pele program. DOE is, of course, integral to our efforts at NASA. We work with the Idaho National Lab, Los Alamos National Lab, Oak Ridge National Lab, and DOE tends to provide technical oversight and support on reactor and fuel manufacturing and providing testing facilities. So very strong relationships with the Department of Energy, Department of Defense, and of course, private industry.
And Congresswoman, if I may also, the Aerospace Corporation is also intermingled with all of the programs that Dr. Myers and Dr. Law mentioned, in addition to our connections with Space Command and the Space Force interests also in this type of technology for national security missions. We're also involved with launch acquisition for all of these projects as well, both for the NASA project and for Draco, which have, more quote immediate, shorter term requirements or desirements for a potential flight test of these types of systems.
Since I've got little time left here, but I do want to ask, how far along are other countries in advanced in space propulsion? Are there any key technology areas in which the U.S. Does not lead?
Bhavya, perhaps. I mean, I can address so Russia has a significant nuclear electric propulsion development program, and they have been talking about launching in the 2030s a significant nuclear electric system. I could not comment on whether or not and how far along they are. I don't have that kind of insight. It does seem to be more advanced than what we're doing today. And perhaps Dr. Lal or other witnesses have other insights.
I would add to that Russia has been launching power reactors for the last 20 or 30 years. So they do have a huge base of an operational expertise that we don't. We launched a power reactor in 1965. And since then, we have not launched any nuclear fission systems. With respect to other countries, there are efforts in China to be developing space nuclear propulsion systems. They have similar goals as ours to be getting to Mars in the 2030s. We don't have too many more details on the specifics, but we can say that China has a very aggressive space development program, and they are seeking to have global parity in this area.
Well, I think my time is up for asking this obvious question. So what can we in Congress do to make sure that the United States stay competitive and compete with Russia, China, and other countries that seem to be far advanced than us?
Congresswoman Kim, since I think we should move on because the time is up, but we're going to do a second round.
Thank you.
You're most welcome to stay for that important question. And with that second round, let me first yield to our chairman, Congresswoman Johnson, if she has any questions.
Thank you very much. No, I do not have any questions at this time.
Great. Thank you, Madam Chair. So let me begin with the second round to be followed by Ranking Member Babin. First for Dr. Chang-Diaz, it seems fairly clear through this last hour plus that without nuclear propulsion, it's going to be very difficult to get to Mars and back and to manage the cargo and to run the stuff that's on the planet itself. Is this actually true? Can we think about Mars just using the traditional chemical propulsion systems? Or do we need to double down and understand that one of those versions of nuclear propulsion is sine qua non for going to Mars?
Well, my personal opinion is that you can go to Mars today if you want to with chemical rockets. I mean, we know how to. The physics will allow you to do that, and but it will be a very fragile mission, and it will be a mission that any contingency would be would put the astronauts in peril, and it could be a really bad day. So to me, it is important that we do the homework and we do it right, and we take a little longer to get to Mars, but do it with a very robust frame, technology infrastructure. And I was going to say in all these discussions that I really believe the moon is a crucial component of this whole architecture, and particularly for nuclear electric propulsion. When you're talking about multi-megawatt rockets, plasma engines, we're not going to test those engines on the Earth. Most likely, you're not going to test them in flight either. You probably will have to test them on the surface of the moon. And we may have to set up a facility on the moon to fire these engines for the full duration of their burn, which would be months, and verify that in fact they do work and they're reliable. So
Dr. Chang-Diaz, that's a perfect pivot to my question for Dr. Myers, because I thought one of the biggest things I took out of your testimony was the need to be thinking about testing these engines on Earth, full scale, rather than trying to test them in space. Can you expand on that? And especially, I don't know whether it's Mr. French or Mr. Meholic talked about the impossible regulations on Earth right now, or Dr. Chang-Diaz's notion we have to test them on the moon.
So we did not find it to be impossible to test on Earth. And I personally have spent months thinking about this and doing the analyses with colleagues. I've led teams that have done these evaluations. It is a challenge, yes, but we're talking about human missions to Mars, which will be humanity's greatest endeavor. And so we're talking about an enormous project. Building the ground test facilities, NASA has done studies. I've contributed to, other panelists have contributed to looking at nuclear thermal propulsion ground tests. And it is feasible to do. It's not cheap, but it is feasible to do. And our committee did not find a way to avoid that kind of testing on the ground in order to demonstrate the reliability. Similarly, with nuclear electric propulsion, we found that it was feasible, it is feasible to test certainly the lithium MPD thrusters. It's one of their benefits because they have a condensable propellant. And so in fact, right now, there is an existing facility at the Jet Propulsion Laboratory, which can be used to test a 2 megawatt nuclear electric rocket, plasma rocket, the lithium MPD thruster. Similarly, others at NASA Glenn, there's a space power facility that is in Northern Ohio. That facility can be upgraded, can likely be upgraded to test the Hall thrusters. And potentially, Vasimir, depending on the scale and the modularity that is proposed for these different systems, one of the questions that we need to answer, one of the technical questions we need to answer is how do we, for nuclear electric propulsion, what is the level of modularity that is feasible? And how do we have to test a multi-megawatt engine, or do we put multiple 500 kilowatt engines? And then we can test the 500 kilowatt engines and do a different kind of test for the integration, for example. And so the committee had these debates and got lots of input from the community, again, the government, academia, and industry. And our consensus was that it is feasible. It's not cheap. I didn't say it was cheap, but it is quite feasible. And in some cases with existing facilities to do the ground testing required for the nuclear electric rocket. I think Mr. Meholic mentioned he made some excellent points about, remember the other subsystems, the reactor, the power conversion system, the radiator, the power management and distribution system. All of those systems have to be tested. A key difference between nuclear thermal and nuclear electric is that nuclear thermal is a much more integrated, and it's much more difficult to separate the subsystems so that you can do modular ground testing. You really need to test full-scale, fully integrated systems for nuclear thermal. That was our committee consensus. Whereas nuclear electric, you could break it up into modular pieces. And as long as the interfaces are very well defined and controlled, we found that we could likely, in fact, we were sure you can design test facilities on the ground.
Thank you,
I hope
Dr.
that answers
Myers.
it.
Let's move back to our ranking member who the last time he spoke was delving that exact question. So
Exactly.
Mr. Congressman Babbitt.
Yes, sir. Thank you very much. Mr. Chairman, if I may, I'd like to thank all the witnesses today, but I'd also like to give just a moment of special recognition to Dr. Franklin Chang-Diaz. Because I believe the work that Dr. Diaz and his team at Astra are accomplishing on their VASMR engine will revolutionize space travel and transform the trajectory of our space industry. And so I want to thank you again. And just back to my question that our chairman just mentioned on the state of thruster technology. I know that there's been some significant success, as I just mentioned, in the since the Academy report came out. And I'd like to give Dr. Franklin Chang-Diaz a little bit of time to find out and hear what his thoughts on this is. And so if I will just let you give us a few of your thoughts here, and whatever time you need to take up to my remaining time.
Thank you, Dr. Babin.
Okay.
Thank you very much for your comments. We are very happy with the results that we've obtained. The key on the work that we've been doing is to integrate, to build the entire package and test the entire rocket engine in the vacuum environment. Many of these electric thrusters that are being tested are tested in sort of some parts of the thruster are inside the vacuum, other pieces are outside, and they are not quite ready to be vacuum compatible. And so we have endeavored to package it all and to deliver a TRL5, so a technology readiness level 5 package that will have all the characteristics of something that you could actually fly. And that is something that we're very proud of and has been accomplished thanks to private investment and also NASA support. So this combination of effort from the space agency together with funding from the private sector is changing the chemistry of things, changing the paradigm. Going back to the moon is going to be also a commercial activity. There's going to be a lot of traffic to the moon. And I think that we need to start thinking of the moon as a place of real interesting work, like what we're doing today with the International Space Station that, began as a very, collection of tests, projects, and experiments. Now is becoming a more commercial activity. And to do that, we need to have an infrastructure of high power electric thrusters that can service that transportation path between low Earth orbit and the moon. So I'm trying to think of the entire architecture as we move further and further into the future, and not just about an isolated mission to Mars. I don't want to get us in the same, sort of pitfall of the Apollo program where we just went and landed on the moon, and then a whole half a century passed and we didn't do any more because the race to the moon had been won. We need to do this in a sustainable way so that it continues to progress and move further and further out, with the private sector very much engaged.
Okay, thank you so very much. And I also want to say congratulations on being selected one of Goldman Sachs 100 most intriguing entrepreneurs of 2021 as well.
Well, thank you.
Dr. Franklin Chang-Diaz, good man. I've got a little bit of time left here, so I'd like to direct a question to Mr. French, if I could. Highly enriched uranium, HEU, raises proliferation concerns and restricts the number of private sector organizations that could contribute to developments. Recent proposals have favored high assay, low enriched uranium, or HALEU, to address these concerns. But according to the Academy report, technical feasibility, performance, safety, fuel availability, costs, and schedule considerations do not favor HEU or HALEU. Should NASA conduct a comprehensive assessment of the relative merits and challenges associated with HEU and HALEU? And should that assessment consider how such a decision impacts U.S. industry? Mr. French, if you don't mind.
Yeah, thank you, sir. I'll defer to some other panelists here on some of the technical aspects of that, but I will say that NASA's activities already are on looking at lower enriched uranium options, and that is what industry is responding to and working on. That also aligns very well with the new launch framework and the testing regimes that increase feasibility. So industry is very much focused on a lower enriched uranium framework, and that is what our government partners are looking at and what the partnerships NASA is engaged in. And then maybe I'll hand it off to some of my other panelists on some of the technical aspects there.
Okay.
I would just say that I agree exactly with what Mr. French said. Since the Academy report and even during the Academy report, NASA was reaching the conclusion that high assay, low enriched uranium was fine. It worked fine. It met the performance requirements. And so NASA has, and as you know, industry also has focused on high assay, low enriched uranium. And as we discussed, as Dr. Lal, I think, discussed, that helps with the proliferation concerns and the launch regulation concerns as well. So
Excellent. Thank you.
I think we may be beyond that question.
You bet. Well, my time has expired, Mr. Chairman, so I will yield back. Thank you.
Yeah, thank you, Dr. Babin. Thanks for hanging in there. Let me now recognize again our one nuclear physicist, Dr. Foster.
I'm actually a high energy particle physicist, so I don't have my neutron absorption cross sections memorized the way you all do. But let's say a couple of things. Well, first I want to point out that the advanced reactor designs that are being pursued on the commercial front are almost uniformly highly enriched, low assay uranium. And so I think there's a lot of commonality there that everyone will benefit from. And so now I'd like to change the subject completely. And it's my considered belief that this is going to work, that there is a good, very efficient solution for the high specific impulse, but low thrust, design corner that you need to go from one low Earth orbit to other planets. All right. I am less sanguine about progress that we're making on getting into low Earth orbit. And there are all kinds of ideas out there. And so if I could, with some of my time remaining, maybe starting with Dr. Chang-Diaz, if Congress was to put some money into some of these high risk, high payoff methods for getting stuff into low Earth orbit and without just using the same chemical fuels that Wernher von Braun came to 60 years ago, and then where should we put our money?
Well, I really think that the chemical rocket is a pretty good way to get things into low Earth orbit, and it's hard to beat, particularly LOX and hydrogen, which are non-polluting, and it's pretty nice technology has been developed. But what I think needs to happen is that low Earth orbit is really a staging ground. It really needs to be a staging ground. And what we need to put money into is the infrastructure to get stuff from low Earth orbit to points beyond. And that is most likely going to start with solar, high power solar electric engines, which will then migrate into nuclear electric engines for deeper path into space. But the solar electric option is also a good one for the vicinity of the moon and the Earth. And our company envisions essentially a system of electric tugs, trucks, to deliver all the cargo that needs to be delivered, to build that sort of railroad, that will be able to support operations on the moon, on the surface, and also in what we consider to be the lunar shipyard, which is where we think the ship to Mars will be built. But it's a whole infrastructure buildup that needs to be created. And I think the government has a strong role to play here with the private sector.
So to your question, Representative Foster, there is a lot of private investment going in launch to low Earth orbit, many billions of dollars. And of course, there has been a lot of government investment too, which is why we have, companies like SpaceX and Blue Origin and Rocket Lab.
I mean, SpaceX is using the same chemical fuels that
Yes.
were explored in the 50s, right?
And I think the private sector is lowering cost by, for example, building the entire rocket with 3D printers. If we had to make an investment, I think a better investment other than launch would be on what is it we do once we are in space. I mean, we need to invest in LEO commercialization. We need to, if we are making things in space, to bring it back down on Earth, or if we are making things in space to take them deeper into space. I think we have a gap in that investment. But just to address your question at the core, there are some companies that are working on, centrifugal methods. So there is a variety of investment. And I don't think if we are making a decision on where the government needs to put money, that would be the place to put money. I think we need to focus on active activities in space.
Exactly right.
And if I may, this is another area too, is that these launch companies that Dr. Law mentioned, well, some of the launch companies as well as others, the capabilities that they're developing are actually for fairly low masses to orbit, right? So the kind of masses that we're talking about for these kinds of Mars missions and assemblies are, tens of metric tons, which is very limiting to what kind of launch vehicles will be available by the time frame they're needed to actually deliver that. So we might have Starship, we might have Falcon Heavy, we might have SLS, right? Other than that, these other smaller launch vehicles just may not have the capability to launch the required masses to the assembly orbits.
Okay, I was just thinking 50 years out. Are we going to be sitting there looking at, kerosene and liquid oxygen for big boosters, or, it's whether, that's my reading on why the Apollo program sort of ended up being terminal, is that there were not, whereas the Lindbergh flight was followed by more and more efficient vehicles, there isn't even a factor of 2 increase in the performance of heavy boosters since the Saturn booster. That's what the block I'm trying to see my way around here. Anyway,
but the cost has come down by a factor of 100. The cost has come way down by changing the architecture and changing the production methods, as Dr. Law mentioned. And so from a cost perspective, we have made progress.
And it's just one final point, I think, is even at the terminal end of the Apollo program, there was some number of studies that said if they were to put a nuclear thermal propulsion stage on the upper stage of the Saturn, it could have delivered twice the payload to the moon.
Yep.
Congressman Foster, thank you very much. By the way, we've expanded our narrow topic of nuclear propulsion to so much of space and NASA. So congratulations, this is great. And now I think we'll wrap up with the distinguished Randy Weber, Congressman from Texas. Randy, thank you for your patience in coming in and out, but the floor is yours.
Well, thank you, Mr. Chairman. And I appreciate all the witnesses today and the ability to hop on the subcommittee here. My question is for all the witnesses, whoever wants to weigh in first, but what is the power, and I'm in late, so I apologize if y'all discuss this. What is the power range for the current demonstration of a fission power system on the surface of the moon? And how is that program aligned with mission needs for and potential future government and commercial applications of in-space power, NEP, as well as terrestrial nuclear power? And I'll open it up to whoever wants to answer first.
So I'll go first. I spent a lot of, thank you for the question, because it's actually something I was going to try to interject later on. It did come up earlier.
I'll send you a bill in the mail.
Exactly. Yeah. So one of the things that we did discuss earlier was the need for scaling from the fission surface power, which is currently targeted at 10 to 40 kilowatts or that range, to the megawatt class that we're really talking about for the space nuclear propulsion systems. That scaling is very challenging, and as Greg Meholic has commented, all of these different subsystems have to work together. You've got to have the reactor, the power conversion system, the power management and distribution system, the radiator, all of that for nuclear electric propulsion must work together with the electric rocket. That scaling from 10 to 40 kilowatts to the megawatt class, factor of 100 or so, that's really hard to do unless we really think carefully about the subsystems that we choose to demonstrate and use on the fission surface power systems. So I would, I would want to be sure that the subsystems approach that we use for the fission surface power are in fact relevant to the megawatt scale propulsion systems that we've been talking about. And there are some options which are not scalable. They do not scale. And so we need to not choose those options for fission surface power if we can avoid them. And I'm sure others of the witnesses have things to say as well.
I can add to that, agree with everything Dr. Myers said, and Representative Weber, you have accurately recognized that there's connections between all four systems, right? So we have terrestrial fission systems. So we have all these companies developing new improved ways of developing small modular reactors on Earth for, reducing greenhouse gas warming. There are, we're talking about a fission reactor for Mars, for Moon and Mars, which is in the, the consideration is in the 10 to 40 kilowatt range. But if you want to be doing industrial scale ISRU, extraction of volatiles or water on either the Moon or Mars, you need to have much higher levels of power. So, you're going to the megawatt range. So at some point we would need to go from, tens of kilowatts to thousands of kilowatts. Then there is NTP, where again, the commonality is, there's a reactor in all of these areas. So there are commonalities. And especially if you want to move forward with NTP, it is, it gives a reason to be doing industrial scale ISRU on the Moon. So for example, if you extract water and you separate it into hydrogen and oxygen, now you have, a mission pull for ISRU on the Moon, which for the moment we don't have. And of course, I wanted to make sure that cryogenic fluid management, which is an area where NASA has a lot of investment, it's kind of critical to all of our space applications, right? And then, of course, NEP, as Roger mentioned, it has extensibility from surface power for the moment for science missions, because, if you're looking at 10 to 40 kilowatts, it's not a human rated or human scale NEP system, but it's outstanding for doing science in the solar system, going to Neptune, going to Pluto, and instead of just doing these flybys where we don't collect a whole lot of data, we can go into orbit, right? We can collect more data. So they're all connected, and we really do need to keep this whole of enterprise approach as we think through our nuclear enterprise.
And just in the final closing seconds, I want to thank Dr. Myers for referring back to my comments as well, and for you, Congressman Weber. In addition to what Dr. Myers and Dr. Lal had said, the subsystems that were referred to may have to take a different form for what there's used on the Moon versus what's used on Mars, right? As far as reliability, mass, size, materials, capabilities. One has more gravity than the other, so how does that affect the physics of the process? Fluid loops. So there's all those different things, but there is some level of extensibility across the range there. But each one is going to be very mission unique and very, very sensitive to those requirements.
Well, thank you for that. I guess that's a broad scientific way of saying, stay tuned. So thank you all so much. I'll yield back. Thank
you, Congressman Weber. And we are now at the witching hour. Everyone's had a chance to speak at least once. Thank you very, very much. It's been a terrific hearing with obviously an enormous amount of knowledge, background, and expertise. So thank you very much. The record will remain open for 2 weeks for additional statements from the members and for any additional questions the committee may want to ask of the witnesses. So with that, witnesses are excused and the hearing is now adjourned, and we look forward to seeing you on many future NASA discussions.